Okay, this is the 2023 paper. Question number 1. Nice easy question to get us started off with. In the rocket engine, the fuel components are first vaporized before reacting to form water. Write an equation for the reaction between gaseous hydrogen and oxygen. So, hydrogen is going to react with oxygen, and combustion of hydrogen obviously can only produce H2O. And then we need to balance it, which is probably one of the easiest balancings you can have. I've already got 2 hydrogens, I've only got 1 oxygen, so I just need to put half there, and we're done. Very generous. Then we have a bond enthalpy calculation. So the bond enthalpy of hydrogen is 432. So this is, let me show you there, 432. And then the average bond enthalpy of OH is 460. So in here I've got 2 of those, obviously, because it is OHH. So 2 times 460. And it says, assume the enthalpy change for the reaction in part A is minus 241. Then calculate the bond enthalpy of the O double bond. Okay, so what I'm going to do is I'm going to say that this double bond here is X. So I've got a half times that. So it's just a simple bond enthalpy calculation, 432 plus a half X minus 2 times 460 equals minus 241. Okay, so the sum of the reactants minus the products equals the total. Okay, and then I just solve for X. Alright, so to solve for X, I just need to quite simply do minus 241 plus 2 times 460, take 432, multiply by 2, gives me X equals 494 kilojoules per mole. Okay, which is about, you know, what you'd expect, right? So you'd expect it to be roughly in that region. Okay, the density of liquid hydrogen is 0.071 grams per centimetre cubed. Calculate the number of moles of hydrogen molecules in 1 decimetre cubed of liquid hydrogen. Okay, so we're going to have to do a, let me think, we're going to do a moles equals mass over molar mass. I'm not given the mass, I'm given the density. So I just need to convert my 1 decimetre cubed of liquid hydrogen into a mass. So my mass of H2 is going to be my volume, 1 decimetre cubed, multiplied by 0.071. Oh no, I've got a problem here. Grams per centimetre cubed. So I need to make sure these units line up. So I'm going to convert this, because what I want is I want my mass, I want grams, I'm looking at the mass. So I'm going to convert this into centimetres cubed. So I'm just going to replace that with 1,000 centimetres cubed. So 1,000 times 0.071 is 71 grams. So what that means is, if I've got a litre, 1 decimetre cubed, 1,000 centimetre cubed of hydrogen, it is 71 grams. So then I can just go ahead and put this in here. So that's going to be 71 divided by 2 times 1.008. So I get 71 divided by 2 times 1.008 gives me 35.2 moles. 35.2 moles. And then the next part says, calculate the energy released when the gas formed from 1 decimetre cubed of liquid hydrogen is combusted. And you'll remember up here it says, assume the enthalpy change for the reaction in part A is minus 241. So this reaction here is minus 241 kilojoules per mole. And I've just worked out that if I'm combusting 1 decimetre cubed, that's 35.2 moles. So this calculation quite simply is just 241 multiplied by 35.2. Okay, so if I do 241 times 35.2, I get 8483. 8483 kilojoules per mole. That will be rounded to 8480 kilojoules per mole for three significant figures. Then we have this bit about SpaceX, and it says, in the Sabatier process, methane and water are formed from the reaction of carbon dioxide and hydrogen gas. Write an equation. So, quite simply, I am making methane and water from carbon dioxide and hydrogen. Okay, so let's just go ahead with carbon dioxide plus hydrogen makes methane and water. CH4 plus H2O. And then you just got to balance it. So I've got one carbon, that's fine. Two oxygens, I've only got one over here, so let's put a 2 there. That doesn't affect my carbons, so that's fine. So now my carbons and oxygens are both balanced. And I've got 4 hydrogens here and 4 hydrogens here, so I need a 4 there, and we're done. And then we want the oxidation state of hydrogen in the reactant. Well, that's elemental hydrogen, so that's going to be 0. Oxidation state of carbon in the reactant, so oxygen is more electronegative, so this is going to be -2 times 2 is -4, so carbon is +4. Obviously it's oxidized, so it's going to have a high oxidation state. And then hydrogen in the product is going to be +1. It can't be any higher than that, which means that carbon is going to be -4. So as you can see, what's happened is you should know that reaction with hydrogen is basically reduction, right? So the carbon has gone from +4 to -4, so it's been reduced, and that's what this process is, from an oxidized situation to a reduced situation. And then hydrogen, obviously, by reacting with oxygen, is being oxidized, so you'd expect the oxidation state to go up. It all makes sense. And then we have this question. So it says, you've got to read this quite carefully. It gives you the enthalpy of vaporization of methane and the enthalpy of vaporization of oxygen. And then it says, it gives you this equation, and it says this equation is -890.8 kilojoules per mole. But importantly, this is gaseous methane and gaseous oxygen. But it wants to know what is the enthalpy change when 1 mole of liquid methane and liquid oxygen. It's very kind. It even bolds it for you. You know, it's sometimes I think they wouldn't do that. They would just like let you see if you can notice it or not. So what I'm going to do is I'm going to first write out the equation that it wants you to find. So the equation it wants me to find is CH4 liquid plus 2O2 liquid becomes CO2 gas plus 2H2O gas. That's the equation it wants to know the energy change of. It gives you this. It says CH4 gas plus 2O2 gas then becomes that. And it says that is -890.8. Okay, so you can just see from here to here is the equation that you're given here. Alright, but I want this value here, and I'm told that the vaporization of methane is plus 8.2, and the vaporization of oxygen is plus 6.8 per mole. I've got 2, so I'm going to times that by 2. Okay, and then it's just an energy cycle, right? A Hess's law situation. So I'm going to go to get from here to here is the same as to go from here to here to here. Okay, so it's going to be simply 8.2 plus 2 times 6.8 minus 890.8, which is going to give me 8.2 plus 2 times 6.8, take 890.8 to give me -869 kilojoules per mole. So it by doing it in the liquid form, it releases slightly less energy. And the reason it releases slightly less energy is because it has to do both of these endothermic processes of converting the liquid to the gas. So you get slightly less heat out of it. So, like I said, very nice, easy question to get you started in 2023.